good morning, good afternoon, good evening, everybody. And it's my great pleasure to introduce my good old friend, Dr. Sang-Hee Wang today. And Dr. Wang is an associate professor in the Department of Mechanical Engineering at the University of South Carolina. Dr. Wang received his PhD from Seoul National University in 2004. Prior to his academic appointment in 2016, he contributed multiple research projects at Princeton University in the area of surrogate modeling development, experimental characterization, detailed and reduced kinetic model development, screening methods for petroleum-derived and alternative jet fuels, biofuel kinetics, plasma-assisted combustion. At USC, he has continued working on jet fuel combustion-related topics with a particular emphasis on near-limit flame dynamics, including experimental studies on the characterization of fuel chemical and the physical properties and their impacts on near-limit combustion behaviors. Okay, Sang-Hee, the podium is yours.
Thank you for nice introductions, Wenting. And it is great honor for me to having a chance to give talk in this platform. So the talk of today, my talk is going to be about the laws of chemical kinetics of liquid fuels on near-limit combustion behaviors. So back in time, I got my PhD in 2004 at Seoul National University with the Soko Jung. Professor Jung was my PhD advisor. At that time, I did mostly flame dynamics, looking for lifted flames and how they are stabilized in laminar flow and then turbulence flow. What are the impact of fuels at the time? But my understanding on fuel chemistry was basically laminar flame speed. That was all I knew at the time. And after that, I joined the Princeton University as a postdoc to work with Lee Kwang-ju. And I realized that I had to start from the scratch to learn a lot of kinetics. At the time, our project was looking for jet fuel surrogate formulations. So it forced me to study chemistry a lot. Although I chose mechanical engineering because I didn't like chemistry, but nowadays I see myself doing more than half of my work is related with combustion chemistry. And it's a great honor to give talk in front of a lot of real chemistry people here. So from my view as a mechanical engineer, the combustion chemistry is always annoying. So I set it parasitic to near-limit flame dynamics. It appears always at the limit, and they control the combustion behaviors at the end, but it comes with very convoluted way. So it is very hard to identify how much combustion chemistry actually really controlling the combustion behaviors. So today in my talk, I will try to minimize the chemistry word. So I'm gonna use simple terms to describe combustion chemistry happening in mostly multi-phase combustions. So recent trend of the advanced combustion technologies always trying to achieve goals to have high thermal efficiency and fuel flexibility. And also we want to reduce the pollutant emissions. And nowadays, considering the climate change coming from the CO2 emissions, there are a lot of fuels being introduced to make more cleaner or hopefully the carbon zero. So as you can see, as we go to the advanced combustion techniques, one example is HCCI combustor. And I heard Mazda has launched kind of HCCI engine car nowadays on the market, but at the end, it's improving the combustion efficiency by boosting the pressure. And then also once you go to HCCI engines, actually your ignition timing is completely controlled by ignition propensity of the fuel. So once you design the combustor to operate at near limit conditions, such as high pressures and low temperature, it suddenly becomes very, very sensitive to the combustion chemistry, as we all know. And the fuel properties at the time becomes 8 predominant factors. Whether you can vaporize, once you vaporize, whether it's gonna ignite, how fast it can propagate within the time domain the engine requires. And then also nowadays, we do see the huge utilization of natural and shale gas, and there's continuous effort to produce the net carbon zero biofuels. And recently, ammonia is another hot topic. since it doesn't contain any carbons. But if you look at the fuel flexibility and low pollutant emissions, whether we're achieving that or not, here's the one example. If you see the H3 ratio and the smoke point, those are the regulated fuel kind of chemical properties currently for the jet fuels by ASTM. And you can see this rectangular box is the petroleum-derived jet fuels variability in that domain. So it doesn't vary much, but once you're starting to look at the alternative jet fuels coming from the natural gas, biomass, fat, and they're even mixing half and half with a lot of these petroleum fuels, you can see the properties are completely outside of the traditional understanding on how the jet fuel is going to burn in gas turbine. And this is also another example of cheating. It's very sad to have that accident, but still it is indicating that we can achieve high efficiency by manipulating the conditions, but same time, limiting the pollutant emission is also very, very challenging to do so. So what are the challenges in combustion science and engineering? So we all know it is multi-time length scales problems. So starting from continuum mechanics, looking at the macroscopic behaviors, you might want to do DNS simulation, or you can do experimentations. And then once you go smaller length scales, now we're getting into the molecular dynamics and then quantum mechanics. And then those chemistry model being in the interface to relate this quantum mechanics to the continuum mechanics. So by principle, by describing the reaction steps in elementary descriptions, actually it is already reducing the complexity, but to do that, we're ending up having a lot of number of species and reactions. So this is the famous figure from Professor Low and then Tenfang Lu, long time ago, showing that the relationship between the number of species and then reactions in the detailed chemistry models. So basically, this excessive number of species reactions are not allowing us to use this detailed chemistry model in an applied CFD. And this star is the example of our model. We ending up producing the real fuel 3 models for the jet fuels, but it does contain around more than 3,000 species and then more than 10,000 reaction steps. The another issue is the most of the case, once you're looking at the liquid fuel combustion, everything is happening in multiphase combustion behaviors, where we have strong coupling between phase dynamics, phase change. Furthermore, we have turbulence chemistry interactions, and then we have combustion chemistry, all messed up all together to dictate the combustion behaviors in applied combustors, as you can see. So going back to the real fuels, I'm using jet fuel as an example here today, since I've been looking at the jet fuels more than 10 years. So real fuels are complex chemical mixtures containing more than 1,000 species itself. Here's the one example of two-dimensional GC by GC measurement for the one of the diesel fuel. You can see there are lots of species and the molecular classes. Once you're getting into the alternative jet fuels, it adds more complexity, although it doesn't contain the aromatics, but now you're getting ability to tailor the molecular structures. And then so far, we do not have good understanding of how we're gonna optimize the molecular structures and compositions in alternative jet fuels, which might be giving us benefit for improving the thermal efficiency and also reducing the emissions. So just looking at this, a lot of molecules, the question is how to characterize the combustion characteristics of this kind of complex chemical mixtures. So combustion chemistry from the engineering perspectives, we heavily relying on the empirical understanding of the potential field property impacts on the specific combustor configurations. So we have been using the combustor indicators or fuel physical property indicators. So depending on what kinds of fuel we are getting, mostly from the petroleum, or if we're starting to look at the bio or alternative fuels, it is a lot of flexibility because you are just making it with your chemical processes. But if you look at the other side of the combustors, whether it is using these spark ignition engines, gas turbine, diesel engine, if you look at the ASTM specification for each fuel categories, there are a lot of fuel property indicators. Most of them are not direct measurements. Examples are resource octane number, the molar octane number, those are the all indicators for the ignition propensity. C10 number, C10 index. C10 index is not the direct measurement. It's coming from the correlation utilizing the boiling temperature and the density. We can use derived C10 number if you can measure ignition behaviors in ignition quality tester and densities, viscosities. Those are all based on the empirical understanding that, yeah, in gas turbine, if we cannot vaporize, we cannot burn. So we have to regulate the initial boiling temperature and the final boiling temperatures. For JP5, mostly they are using in aircraft carrier where temperature is extremely hot. So they didn't want to have explosion while feeding the fuel into the jet fighter. So they are regulating the initial boiling temperature. So ending up JP5 becomes a little bit heavier. And there are a lot of regulations in terms of emissions, benzene, sulfur, and many other stuff, which are not direct measurement of the engine performance based on those fuels. Those are speculative limitations. If we look at combustion chemistry from the scientific perspectives, we have been trying to develop detailed chemical kinetic models more than many decades. So we're starting to look at simple system where we can do the high-level quantum chemistry computations for small molecules. We can define those rate constant quite accurately nowadays, thanks to many progresses made from the chemistry side. If we're looking for heavier liquid fuels, the distinct nature of each molecule becomes smeared. When you go to large molecules, allowing you to use rate rules. Those are the principles for the large molecules currently pursued by Lawrence Livermore. And some of the elementary reactions, allowing us to measure them directly through the smart experimentations. Once we do that, someone might want to develop surrogate mixtures based on whatever methodology to come up with the number of species to be included. But once you look at the multi-component jet fuel model, it is built on based on the core chemistry from C0 to C4. And then there are lots of sub-component chemistries, including N-alkanes, iso or weakly branched alkanes, cycloalkanes, aromatics. If you're looking at the gasoline fuels, you might need to include alkenes. And then nowadays we do have oxygenate ethanol being part of the gasoline. So you have to do the ethanol combustion chemistry. You have to add on. If you are looking at the diesel fuels, there will be the double-link structures, double-link cyclic structures, leptins. So those are the most complicated fuel molecules to build chemistry model, but there are huge effort going that directions. And once you do that, you might be ending up having really big chemical kinetic models. In my case, for the jet fuel, it was more than 3,000 species, more than 10,000 reaction steps, which takes roughly 1 hour to compute zero-dimensional transient ignition delay time at one conditions. So this is annoying. So now there are a lot of progress being made to reduce the detailed chemistry models, either using the restricted temperature pressure conditions, direct ref DRG. There are a lot of versions of DRG, and then path flux analysis, which was developed by Yiguang's group with venting. And maybe you can do CSP or lumping. And then we are hoping to see that at the end of the day, we can produce a useful jet fuel model, which can be used in multi-phase, multi-dimensional CFD simulations. The challenges are actually none of these categories are perfect yet. The rate rules has been revised multiple times. It still needs to be revised if my understanding is correct. And also there is the big question mark in terms of multi-component jet fuel model. whether the combustion during the combustion field specific the chemistry subset might be interfacing to each other or intercommunicating to each other, such as NialKane fragments interacting with isoalkane fragments, which might be important to predict soot formation at the end of the day. And then also if you use surrogate approach, whether surrogate mixtures are really representing that real fields, your target field, that is also a known question mark. And then we spent a lot of time to develop very accurate high fidelity core chemistry from C0 to C4, but unknown question answer is that how much we need to include for the core chemistry. Do we need to include C5 or C6? Those are the main gateways relating the field chemistry subset to the core chemistry as well. And those are all unknown. And then what are the state of art of model reduction method? Can we bring it to the really small number of species, which can expedite the use of multidimensional CFD? If I go to the multiphase combustion, it becomes more ugly, but I can see it might be giving us a little bit better idea by looking at the time scales. So we know that if you go to multiphase combustions, that field boiling characteristics will be part of the game. If I do time scale analysis at 800 Kelvin with initially 10 micron droplet size spray, which is actually really smaller than the real spray actually produced, which are around 20 to 100 microns in most of the case. So we can come up with 3 time scales, flame time scales, which is a function of the laminar flame speed and then flame thickness. If you go to high pressures, your laminar boiling velocity goes down, where your flame thickness is getting thinner and thinner, it's canceling each other. So you can see nonetheless constant flame timescales. If you consider the vaporization timescales, it's starting to increase as increasing the pressures. That is mainly coming from the time required to heat up the droplet to achieve certain boiling temperature. As you go to higher temperature, your boiling temperature goes high, as well as your overall vaporization timescale predicted by the d-scale rule is getting longer. So once you increase pressure, your vaporization timescale goes up. Finally, we have ignition timescale coming in, thanks due to the collisional frequency being increasing by increasing the pressures. So the overall ignition delay time gets shorter and shorter as you go to the high pressures. So playing with these 3 timescales, we can expect there might be 3 regimes. The first one is the fully vaporized combustion regime, where the vaporization timescale is too short compared to any flame timescale. Then you can assume that it's going to be governed by gas phase combustion chemistry, mostly flame chemistry, if it is forming a flame. Regime 2, when your vaporization timescale gets longer than flame timescale, which might be relevant to gas turbine operations, then you can expect there might be multi-phase combustion regimes, and there might be preferential vaporization impact, which I will be discussing further later. But preferential vaporization impact is that is the considering the change of field chemical properties in a function of boiling temperature. So when you have the partially vaporized droplet from the spray coming in, then there will be, if there is the preferential vaporization, then what are the gas composition coming from the multi-component fields? Those might be impacting the combustion dynamics at regime 2. If you go to the regime 3, now ignition delay time gets a lot shorter than any time scales. Then we can see there might be multi-phase or gas phase ignition chemistry regime. So once we put them all together for the jet fuels, here I just picked endodecane to represent jet fuel range. Then you can see considering the most of the gas turbine operation condition is around, depending on what you're looking at, but sometimes around 10 atm or 20 atm. You can see most of the combustion behaviors is happening at the regime 2, where the multi-phase combustion chemistry is happening. If you look at the gasoline here, it is so easy. I'm using it as an heptane. It's vaporizing quite quickly, so the vaporization time scale is very short. So you can see up to pressure range where the spark ignition engine operates. Everything is just governed by gas-based combustion chemistry or flame chemistry. If you go to the diesel range using an hexadecane as a representative diesel fuel, now you can see, considering the injection pressures and the engine conditions, it's mostly operating at regime 3, where multi-phase ignition chemistry dictates the behaviors. So challenges in multi-phase combustion is that first of all, the chemical kinetic characteristics of liquid fuel is high dimensional chemical complexity involving thousands of species, more than 10,000 of reaction steps. Then the question is, can we develop a alternative low dimensional approach, but still retaining the fundamentals? So I've been utilizing this chemical functional group approach, which will be introduced soon. And the other one is the complicated interaction between combustion dynamics and chemistries, and how we're gonna convolute those interactions. The answer is we have to do very smart experiments, even for us to look at what are the role of chemical property impacts on those multi-phase combustions. The next question is, if we know what are the governing parameters in combustion chemistry, then can we develop or produce really low dimensional, reduced or compact chemical kinetic model, which can be used in applied multi-phase, multi-dimensional CFD. And then hoping that once we do this compact chemical kinetic model, we do provide its capability and limitations. So the engineers won't be extrapolating with this compact model, which has intrinsically limiting capabilities. But by doing so, once we do see some result coming from the multi-phase, multi-dimensional CFD, not agreeing with experimental data, then we might be able to answer the question that where the deficiency is coming from. So chemical functional group analysis, those are the organic chemistry 101, everyone knows. The jet fuels contains alkanes, isoalkanes, cycloalkanes, aromatics. It doesn't contain alkenes much, and there's not much doubling structure molecules either. And we know that each molecular class plays different roles depending on its molecular weight and particularly isomeric structures. But once you're starting to look at the measurement coming from GC or GC by GC, it just cannot differentiate those detailed isomeric structures accurately. So just mostly just lumping as aromatic, although it does have long alkyl chains. That has been the challenges in that approach as well. But once we use chemical functional group approach, it suddenly becomes low dimensional descriptors. We just need to look at a few, roughly 7 or 6 functional groups pertinent to the jet fuels. It does simplify since it is very low dimensional descriptors, small set of functionalities. And the good news is that we can quantify those functional group quantities by interpreting the proton and then 13 carbon NMR spectra together. So here's the example for the Jet A. You can see from the proton NMR, I see the CH3 peaks, CH2 peaks, and the aromatic peaks, depends polyaromatic peaks at the end. If you look at the carbon spectra, it does give a lot more information. But the challenge is that whereas the proton NMR can be very quantitative all the time, but in case of carbon spectra, you have to spend a lot more attention to get semi-quantitative natures from the spectra. By doing so, we can define the CH2N as more than 3, the methylene group combined all together. We have CH3 groups, we can have benzyl type groups, we have CH2 cyclo groups. We can all differentiate from the proton and the carbon spectra. Here's the one example. In case of Jet A PSF 10 3 to 5, Jet A, I see the CH2N groups are really large portions together with methylene groups, CH3, methyl groups. And then there are some isolated CH2 groups, and there also CH and the CH2 cyclos. Benzene types only contain only 2% in a mole fractions. But the reason I have only 2% of benzene type, in functional group analysis, even though the JFL contains around 20 to 25% in liquid volumes of aromatics, those aromatic structures in JFUs, they are highly isolated. So if you just count the benzene ring, then ending up being only 2% in mole fraction. But if you combine them all together, looking at the isolated structure, it suddenly becomes around 20%. And then JP5, which is a little bit slowly burning fuels, but it says it has a lot more methyl groups compared to CH2N groups. So rough understanding of combustion chemistry in low temperature or high temperature. If you have lots of CH2N groups, it's mostly coming from linear alkanes. It promotes reactivities through thermal decomposition at high temperature, since the bond energy here is relatively weaker than others. So it's easily dissociating and creating very effective radical pool. If you go to the low temperatures, those are the cells performing the RO2 and then consequent QOH and the O2 QOH, those kind of pathways for low temperature chain branching reactions. And also CH2 has relatively weaker bond energies to others. So it might be inducing the thermal decompositions to promoting the reactivities. If you have a lot of methyl, it's coming from the either isoalkanes or weakly branched isoalkanes or the terminal position of the N-alkanes. That requires a lot of H abstraction reactions by utilizing the radicals, mostly through chain propagation reactions. So it's not much promoting the reactivity. Cycloalkane structure is very interesting. If you go to high temperature, it is easily breaking down through the ring breakup process. After doing that, it suddenly becomes quite similar to N-alkane chemistry, undergoing multiple layers of the thermal decomposition, populating ethylene and the radical pools. But if you go to the low temperature side, it just doesn't allow to have low temperature chain branching reactions easily due to the cyclic structures. Finally, the benzene type stems from the aromatics. They are really slow. They are actually radical scavengers, and it does have do-loop between the initial parent, the aromatic molecules going through the H abstraction, but there's the radical recombination reactions eating the radicals continuously, so it is slowing down the overall reactivities. So we define these functional group descriptors. Then next question is, can we develop the low dimensional, the quantitative structure property relationship, so-called QSQR regression model, which has been very popular approach for another disciplines, such as biomedical approach. They do a lot of experiments. It's kind of big data, putting them all together into the black box, going through this whatever algorithms, as you want to say, AI or neural network, whatever, they're coming up with regression models to identify the impact of certain molecular structure on any performance. So we do the same thing here. So there are a lot of experimental results published in the literature for homogeneous reflected shock ignition delay times. So we're just following the Arrhenius expressions, employing this functional group distribution together with temperature, and then we optimize the models. Then you can see, you can optimize the model to predict the ignition delay time of homogeneous ignition delay time. And once we do that, we compare what are the relative impact of functional groups by performing the sensitivity analysis. So as you can see, we see a lot of contribution from CH2 to promoting the ignition behaviors or shortening the ignition delay time. But as you go high temperature, their kinetic contribution starting to disappear. And then also the aromatic start is always delaying the ignition delay time. And growth features are well captured compared to the detailed kinetic model predictions. But what's the beauty of this regression model is we can right away identify what are the relative contributions from thermal impact or chemical property impact of the fuel. So here's a solid line predicted by these QSPR regression models. If you go to the real low temperature or really high temperature, the thermal impact is dominating. But if you go to NTC regime, then you can see the chemistry impact starting to play a role. And if you compare to the detailed model predictions, it does indicate similar behaviors, but detailed model approach further emphasizing the chemistry impact at the NTC regimes. On the other hand, okay, we can do the same thing to relate those functional group approach or distributions to the applied indicator, such as derived C10 number, which are normally measured in a high pressure, constant temperature, the constant volume chamber by injecting the fuels using the diesel injector, measuring the ignition delay time between the onset of fuel injection and then the ignition delay time, which contains a lot of stray dynamics. But after that, you do calibrate against the reference fuel, and then you're getting the indicators for the fuels. So we produce QSPR regression model for this derived C10 number. As you can see, we do have pretty good high fidelity by using the functional group distributions. Once you do that, we can find out why our surrogate approach previously proposed, which was using the derived C10 number as one of the target to match. So there was a lot of questions why DCN needs to be involved for the jet fuel. Normally, the derived C10 number is not the applied combustion indicator utilized for jet fuel range for the ASTM specification. But if you look at just performing this statistical analysis, I just provided large number of random mixtures with the endodecane, isooctane, and propylbenzene, and this 135 tribenzene mixtures. And you're starting from around 176,000 mixtures. And then I say, if I impose the criteria within some uncertainties of each combustion target, what are the number of mixtures meeting that criteria? As you can see, if I starting to add more and more, the number of mixtures which can satisfy those targets as a surrogate formulation getting smaller and smaller. If you look at the changes of functional group distributions, you can see as I go to the four indicators as a constraining targets, I'm really minimizing the variability of each functional group distributions. At the end, if you compare, so I have roughly 200 mixtures or 1,000 mixtures satisfying as a surrogate mixture for 8 jet fuel. But if you look at the variability of this surrogate mixture, you can see it is quite effectively constraining the distribution of chemical functional groups. Particularly if you look at the other case, only using the HC as a target, which is one of the ASTM standard, then you can see it is just cannot constrain the variability of CH2N functional group, which play important role in overall combustion behaviors. But once you're starting to use DCN, which has very high sensitivity to the CH2N functional group, is constraining the variability and ending up getting uniform A-specific functional group distribution, which can be emulated by many numbers of the chemical compositions. You can change scanalkane from endodecane to an hexadecane, but you can still regulate those functional group distributions. So we got the questions from the NJFCP at the time, looking at the jet fuels, trying to understand the relative impact of cycloalkane functionality. So that if you produce alternative biofuels from the biomass, you can produce high cycloalkane containing jet fuels, which is promoting the overall energy density. So we utilize this approach, and then we took NMR spectra for Shell CPK, is cycloparaffinic kerosene. You can see there's a lot of cycloalkanes coming here in protonate response, as well as certain the area in the carbon spectra, and then we are comparing to the another shell. The alternative jet fuels is SPK, is produced from the gas to liquid. Then once you plug in quantifying the functional group distributions, you plug into the QSPR sensitivity analysis, you can identify what are the relative impact of cycloalkanes in combustion chemistry. So the current regulation is up to 50% mixed with the petroleum jet fuels. Once you do that, you still see not much impact coming from the cycloalkanes compared to other functional groups, particularly CH2N groups. So it says combustion behaviors mostly still governed by CH2N functionality, where it dictates the reactivity. At high temperature, some of the composition play a role, and low temperature side, it does have the QOH, RO2QOH formation route is the major the chemistry pathways for the combustion chemistry. Once we do that, we can simply compare the potential impact of some of the applied indicators. So as you can see, if the red one is the shell SPK, so it does have higher DCM because it is containing a lot of CH2N functionality. So it has higher reactivity, but you're starting to mix with jet fuels, your drive C10 is changing, and 50-50, it suddenly becomes within the jet fuel variability. And in case of shell SPK, it is really good because in terms of chemical properties, still within the variability of jet fuels, indicating that this shell SPK we might be able to use right away in any gas turbine if we believe that DCN is good combustion parameters to constrain the jet fuels. But another interesting point is the threshold shooting index. That is indicator of how much soot is going to form by mixing them. So another one way to look at it is, yes, it does have high energy density, but it does have higher sooting propensity due to the existence of the cyclostructures. So it doesn't reduce much the soot emission propensities, whereas if you use shell SPK, it's substantially reducing the sooting behaviors due to the not much having aromatics in the beginning, and also do not have cycler component either. So those results can be used as an effective initial screening tool, where the alternative jet fuel producer has only limited volume of mixtures. Then we can do the NMR analysis utilizing QSPR regression models, and then we can assess that this fuel has promising future or not before going for large quantity productions. In multiphase combustions, so I had a chance to collaborate with Tim Lewin's group at Georgia Tech to look at the impact of the fuel physical and the chemical properties in lean blowout in model gas turbine combustors. And the initial observation was at the time that those two fuels, particularly for ZA and JP5, even though there is around 10% difference in terms of DCN, but it does give almost identical lean blowout behaviors. I'm going to explain how they took the lean blowout experiments later in the details, but there was the question mark. So everyone says the right C10 number could be a good indicator, and then there are recent publications suggesting that ignition, the drive C10 number has linear relationship to the LBO equivalence ratios. It suddenly brings us some question about preferential vaporizations. So we prepared 5 distillation cups, putting the jet fuel into the ASTM-D86 distillation device, and then we produce 5 distillation cups, as you can see. If you go to heavier end, it might be the place we are condensing some additive packages. So color does change from the transparent color to already yellow. But you see there's roughly, and then we took the derived C10 number using the IQT, and you can see there's roughly the 10 to 15 derived C10 number changes in a function of, let's say, zero boiling temperature. That immediately suggesting that maybe preferential vaporization, looking at the initial derived C10 number being quite similar to each other, that might be the reason why these two fields have ending up giving us similar ABO equivalence ratios, where the fuel being sprayed into the gas turbine combustor, the not 100% of fuel being fully vaporized before hitting the flame zone. So it's partially vaporized and there is preferential vaporization, then that might be the reason why we're ending up getting similar behaviors. So from there, we did same experiments for other jet fuels as well as alternative jet fuels. So it's quite interesting at the end. Most of the petroleum-derived jet fuels shows 10 to 15 the variations of derived C10 number changes. If I say delta DCM from the initial cut to the final cut is the preferential vaporization potentials. But if you look at the alternative jet fuels, they are all over the place, actually. More interestingly, this HRJ, which is coming from fat, tallow, or camelina, it does have substantial change of derived C10 number changes. One example for camelina is that I have 40 derived C10 number changes, which is extremely large, actually. So we can explain why by looking at the functional group changes. Most of the petroleum jet fuels, if you go to heavier end, you're losing the benzene type. It's going to disappear, and then your CH2N groups starting to picking up, and then your metal groups going down, all suggesting that ignition propensity or combustion chemical reactivity is going to be faster at the heavier cut. And the other case of shell SPK, IPK, those are mostly coming from the FT process. Initially, you produce the syngas, hydrogen CO, and it goes to the another process of FT process to produce liquid fuels. Actually, they don't exhibit any the preferential vaporization potentials. And if you look at the functional group distributions, actually, they are almost identical in terms of the chemical functional group distributions. And you can see also HRZ camelina has a lot of picking up of the CH2 functionality as you go to heavier end, while the CH3 groups, methyl group goes down as you go to heavier end. That explains why there is huge change of derived C10 number between the initial cut and final cut. So going back to the relative impact between fuel chemical and the physical properties on rim blowout. We know it's going to be governed by both fuel physical and then chemical properties. So in early 80s, Lefebvre from Purdue University performed a lot of measurement with the petroleum jet fuels. His conclusion was fuel physical properties actually impact the overall combustion behaviors because it has to be vaporized before getting into the flame. But as I mentioned before, there's recent studies suggesting that chemical properties the indicated by derived C10 number has linear correlations to the rim blowout behaviors. So we got opportunities to formulate fuels and then testing in rig scale ABO, the Georgia Tech rig scales. Here's the schematics, how it works. I'm not gonna go details, but it's just dumping a lot of fuels through the spray injector into the combustor, and then they are slowly reducing the fuel flow rate until they see the rim blowout happening. In that case, there's the radiative thermal feedback going back to the injector. They define it as bulkhead temperature. It's going up. So they tested 3 cases of the air inlet temperature from 300 Kelvin, 450 Kelvin, and 500 Kelvin. As they increase in the air inlet temperature, it's promoting the vaporization of fuel sprays. And they took multiple measurements. I'm getting this doing statistical analysis, looking at the average values of determined equivalence ratio at LBO, using as the final values of LBO. So we tested N-dodecane versus one of the alternative jet fuel, which is GVO-ATJ, which is coming from the alcohol to jet fuel, alcohol to jet through the oligomerizations of the isobutanes, actually. So it is exclusively a mixture of isododecane and isocetane. Both of them have very similar chemical behaviors. And we tested ignition delay time was identical to isooctane and isocetane. And isododecane being found. And then as you can see, there's no change of the derived C10 number in a function of the boiling temperature. Here's the summary of the field properties comparing to the derived C10, the N-dodecane versus GVO-ATJ. Everything got very similar in terms of H2 ratio, molecular weight, boiling temperature is quite similar. But the big difference is the derived C10 number. One does have around 73, the other one has around 15.5. So by taking the ABO at Georgia Tech's model combustor, we see it depending on air inlet temperature. When you go to the room temperature conditions, everything is convoluted due to the turbulence and the multiphase combustions starting to play a role. So there's not much change between two fields, although it does have huge change of chemical properties. But as it goes to higher temperature, where the field being photo vaporized and then getting into the near fully vaporized conditions, then we do see around 10% changes. And considering that LBO, the first order impact of LBO behavior is coming from the balance between incoming flow and then overall combustions, turbulence burning velocities, which is a linear function to the laminar burning velocity. The N-dodecane and then GVO-ATJ is around 15 to 20% difference in laminar burning velocities. That explains around 10% of the LBO changes between two fields. So we got opportunities to mix large quantity of surrogate mixtures. So at the time, I was very excited. So I prepared two mixtures, and then this two fields being produced from the Air Force lab, thanks to the Dr. Tim Edwards. One is the N-dodecane isooctane and then 135 TMB. The other one is, instead of using the N-dodecane, I put N-hexadecane to manipulate the preferential vaporization potentials. So compared to the target fields, so this surrogate 2 containing N-hexadecane, it doesn't vaporize N-hexadecane in the beginning. So it has really low DCN compared to the other two fields. But if you go to the fully vaporized conditions, they becomes almost identical in terms of combustion property targets. And then their functional group distributions are almost identical. So the test got done at Georgia Tech. Here is the comparisons. So at 300 Kelvin and 450 Kelvin, where the field being still partially vaporized, we do see the big difference compared to the target fields. However, if you go to the 550 Kelvin, it's getting into the fully vaporized conditions, suggesting that both surrogate mixture can emulate the target fields. Whereas if you go to the lower inlet temperature, there are differences coming from the preferential vaporization characteristics of these two surrogate mixtures. So as I mentioned before, everyone's suggesting the CNA is good parameters for LBO. We see linear behaviors, but once you use the initial DCM value, the DCM value of the initial distillation curve, now we see it's improving the I-square value, suggesting that preferential vaporization still playing a role, important role for determining the rim blowout behaviors. But the question is, the correlation doesn't indicate the causations. The results suggesting that the preferential vaporization being important, but what is the first order governing physics in LBO behaviors, which is not clearly answered yet. So to answer that, we developed the new burner lab scale experimentations for fundamental investigations to look at the impact of preferential vaporizations, and mostly happening laminar flow regime using the movable fuel injector. This injector can go up and down, and then I can change the burner temperature to control the extent of fuel vaporizations by manipulating the flow resistance time and the burner temperature using schematics. By doing so, if I go to longer resistance time, I'm getting kind of fully vaporized fuel combustions. If I go to shorter resistance time at 450 Kelvin, I'm starting to see the flame being extremely perturbed by the random and local field droplet vaporization happening at the flame surface. So we define the extent of field vaporization by measuring the spray properties using the PDPA, and we can define the fraction of fuel being vaporized by utilizing the initial fuel flow rate we dumped, and then the ratio between the effective area ratios between the nozzle and the PDPA measurement volumes. So as you can see, if I go to the longer length side, my droplet diameter getting smaller and smaller, indicating it is getting fully vaporized. And then also the response from the PDPA, the frequency of the data acquisition is going down, and then plugging them together. So now I can see, oh, I'm partially vaporizing, and if I go to around 2 milliseconds, 2 seconds, I'm fully vaporizing the mixtures. So I can control the extent of vaporization to measure the combustion dynamics happening due to the partially vaporizing characteristics. So we did fully vaporized conditions by bringing the burner temperature around 700 Kelvin. We also found there are two regimes of flame flashback behaviors. One is the propagation-driven, the other one is ignition-driven flashback, which is quite similar to what we observed in Igwang's lab using the LADS burner at the time. So by function of equivalence ratio, if you go to rich case, you see there are sudden ignition current happening at the exit of the burner. So suddenly bring the flame inside of the burner, indicating flashback happened. And if I change the N alkanes from the N-heptane to the heavier one, the transitioning equivalence ratio becomes lower and lower, indicating that low temperature ignition characteristics is governing these ignition-driven flashbacks. So we formulated two fuel mixtures to be smarter, to see what are the impact of preferential vaporizations. So we mixture one is the N-octane and isocetane mixtures. The other one is the N-isooctane and then isocet, isooctane and then N-hexadecane mixtures. So by manipulating the mixture ratios, we can find out the identical CH2N to CH3 ratios, which suggests, and then we ending up getting very similar DCM values, suggesting that fully vaporized combustion behaviors, those two fuels, mixture 1, mixture 2, should be giving us identical behaviors. If you take the measurement as fully vaporized condition, you can see those two fuels giving almost identical behaviors, showing us the ignition-driven flashback behaviors as well as propagation-driven behaviors as the conforming test. Once you go to the lower temperature at 450 kelvins, now we have to consider impact of field vaporizations. There is the local random field droplet vaporization happening near the flame surface, but ending up perturbing the flame structures, increasing the effective burning area, thus it is increasing overall burning velocities, and then my flashback burning, the velocity gets higher and higher. And then also partially vaporized field vapor alters local equivalence ratios. Locally, it might be changing laminar burning velocity locally, which is coming from the preferential vaporizations. So to characterize that, we just took the PDPA measurement and then coming up with the vaporization fractions in a function of resistance time. If I compare the flashback depth velocity between two fuels, if I go to the fully vaporized conditions, then these two fuels giving almost the same behaviors. But if I go to the partially vaporized conditions, there are considerable difference between two fuels, suggesting that the flashback is actually governing. So as I mentioned, the local flow perturbation increasing the effective burning velocities, and then changing of the laminar burning velocity coming from the local vapor phase field deposition coming from the preferential vaporizations. So the beauty of PDPA also giving us the local velocity fluctuations. That is also linear function of how much you vaporize. And then also we can calculate the mixtures based on the liquid fraction measured by PDPA. We can calculate the laminar burning velocities. So in case of mixture 1, if I go to the partially vaporized condition, I'm only vaporizing N-octane versus isocetane. In case of mixture 2, I'm vaporizing isooctane earlier than N-hexadecane, so ending up giving us around 10% difference of laminar burning velocity depending on how much it got vaporized. And following the Dunkel's analysis of weekly perturbed turbulence premix flames, we can come up with the turbulence burning velocity being scaled with laminar burning velocity with local flow fluctuations. Here I'm just using the measured droplet diameters as a characteristic length scales of the flow perturbations. Then you can see, okay, coming from this large variation of the rim blow up velocity, by normalizing with laminar burning velocity is getting closer. And if I further multiply, manipulate with local flow velocity fluctuation, I'm getting better correlations, but still suggesting that the change of laminar burning velocity locally caused by preferential vaporization is the first order parameters, suggesting that that's the governing physics of flashback in these particular conditions. So the question is then, what's going to happen to high pressures? Our scaling analysis suggesting that as we go to higher pressures, that it's going to augment the preferential vaporization impact at high pressures. To do that, we did simple, not much simple though. Tambio is not going to be happy if I say that, but we did isolated single droplet combustion calculations utilizing 3 mixtures. And in droplet combustion computations, we implemented the mixing characteristics by defining the liquid phase Lewis number, which is comparing to the thermal diffusivity interior into the droplet. The other one versus the mass diffusivity inside. So if I have large number of Lewis number inside, it means I'm not mixing well. There's not much mass mixing inside of the droplet, which means when it goes to vaporize, my fuel is going to vaporize from the surface in the same time, since I cannot provide new, fresh, lighter component to the droplet surface. However, if we decrease the Lewis number, now there's huge mass mixing inside of the droplet. And if I go to the limiting conditions, it becomes fully mixed. So I can always provide this lighter component through the mass diffusion, enhanced mass diffusion to the droplet surface, ending up being able to preferentially vaporizing the fuel component. So this is his calculation result. The long story short, it does impact the preferential vaporization, impact the overall burning rate, where the overall regression rate is not exactly showing these preferential vaporizations. So by computing those behaviors in a various number of the droplet size and the pressures, we define the degree of preferential vaporization impact as a burning rate in the difference between maximum burning rate coming from the preferential vaporizing behaviors compared to the initial, and then normalizing the average values. So here's the result. So preferential vaporization impact goes rather when you go to larger droplet, which makes sense. And then more importantly, the pressure, if you go to higher pressure, there's strong influence coming from the preferential vaporization in the beginning and then plateau out at the higher pressures, suggesting that preferential vaporization becomes more consequential at decreasing at initial droplet size and then increasing the pressures. So here's the last part of compact chemical kinetic model. So now we have experimental evidence that preferential vaporization impacts are important for rim blowout and then the flashbacks. And we also saw there are huge change of preferential vaporization potentials among petroleum-derived and then alternative jet fuels. And numerical simulations suggest that higher pressure is going to be important for at higher pressure, preferential vaporization becomes more important. Then just going back to the current approach of developing a comprehensive and detailed chemical kinetic models, it's really limiting its utilization in multidimensional CFD simulation, particularly for the multi-component fuels. So here's our model, real fuel suite containing more than 3,000 species. So I gave this talk probably 6 years ago in one of the conference in front of a lot of engineers from the industries. So I was able to reduce this detailed model using the PFA and the DRZ up to 200 species, hoping that this might be small enough for them to make a decision to use detailed elementary reaction-based but reduced model can be used in their CFD. And then they said no. They want to have less than 30 species or 50 species. Then the next question is how are we going to compact further? Well, those are the tricky part. So what we did was we defined surrogate by using the CPT approach, matching the surrogate mixtures. We defined the surrogate mixtures, and then we developed the detailed or the reduced chemistry model, which is the assembling of a lot of community effort, starting from the C0 to C4 core chemistries, and adding the NiChem chemistry and the isoalkane chemistry developed from the Lawrence Livermore. We developed some of the aromatic component mixture models, bundled them all together, and then we utilized lumped chemistry subset for the fuel chemistry, and then optimizing those rate parameters, including the pre-exponential the parameters, A factor, and the activation energy within the pre-described uncertainty limits, and optimizing that. Those are the results we got. So by doing so, I can produce around 45 species compact model, which does have core chemistry subset from the C0 to C4, and lumped chemistry model for the fuel chemistry. And then I was able to reproduce reasonably well the ignition behaviors, flame propagations, as well as extinction behaviors. So this might be the approach to develop more sophisticated compact model, which might be able to account for the preferential vaporizations, which can be used in engineering CFD, so you can get feedback from the industries to look at where the deficiency is coming from. So here's concluding remarks. The impact of chemical kinetic characteristics of liquid fuels always coming into the play in a very, very convoluted manner through the coupling with combustion dynamics, spray dynamics, turbulence chemistry interactions, so many other stuff. And I want to emphasize that the preferential vaporization in multiphase combustion has not been fully understood, particularly for the high pressure conditions where experimentation and then diagnostics are still challenging. And it is necessary for us to produce a reduced order compact chemical kinetic model, which allowing us to bridge our outcomes from the fundamental science to the applied CFC communities. So if we can relate our fundamental understanding to these empirical indicators, such as DCN and others, as well as the multi-phase CFT result, it might be allowing us to identify where our modeling approach has deficiency. So my conclusion is to do that, we have to have a holistic approach. It's always important for close the gap between applied science and then applied fundamental science and then applied engineering. Let me give acknowledgement. So I love to say I really thank lucky to have good students in my place, including the postdoc Wei Wang. Now he's currently working at Cambridge, his place at UIC. I've been lucky enough to have a lot of good colleagues, including Tom Beer, Fred, Iwan, Steve, Tim Umbrello, Matt, Wenting, Joe, Jeff Standner. I forgot to include Zhang Chen, but there are so many people I met during my Princeton time. Gave me a lot of opportunities to explore many other stuff. And I also appreciate the funding from Air Force, NASA, NSF, and Hyundai and Siemens. And last year we got funding from CAUST to look at the way to apply this functional group approach into the oxidative desulfurization process, which was quite successful and interesting. So let me finish from here. So more than happy to take questions.
Now, here I received a few questions from the audience and also the panelists.
Okay.
The first question is, we presume that in a reacting system, the time it takes for each species to reach chemical equilibrium it's much shorter than the time it takes for the system to change. How can we link the relatively long time scale at low pressure to apply the equilibrium assumption as seen on slide 11?
Wow, that is tough questions. I don't know how to answer, but my understanding after looking at this detailed model for the real fields, those molecules are pretty large molecules. So their rate constants are almost every time the high pressure limit. I don't have answer for that question. There might be better person in chemistry side to answer that questions. But what I do see is this looking at the low temperature chemistry following the traditional approach has a lot of limitations. But what I want to say is if I can measure the time evolution of functional group distributions during the low temperature chemistry, looking at the formation of RO2 and process isomerization process go for QOH and the OQQOH stuff. If I compute the NMR spectra using those molecules, I do see the potential to take those time evolution of functional group behaviors in low temperature oxidation schemes.
Okay, thank you very much. The second question from Peng Zhao. How does the functional group method deal with the isomeric effect? There is clear evidence that the position of a functional group, for example, a double bond or benzene ring can affect the fuel reactivity, albeit with the same functional group distribution.
That is really good question, actually. So when we did cycloalkanes, including to whatever QSPR regression model, I do see I cannot differentiate those detailed isomeric structures. So where is the alkyl chain being linked to the cycloalkane positions, and then the isomeric structures of the alkylated cycloalkane itself, we cannot do that. But my answer is going to be that relative impact coming from functional groups. So once I include the cycloalkanes in the QSPR regression model, I see the sensitivity to the CH and the C gets larger. But if you compare to those contributions from the other dominating functionalities such as CH2N and CH3 and benzene type, those are relatively smaller in that ignition space. So those are the difficult part. On the other hand, if you really look at carefully the NMR spectra, you can get some hint. One example, if I use the jet fuels, I see we have been using N-propylbenzene or 1,3,5-trimethylbenzene as a surrogate component. That doesn't allow us to reproduce the real jet fuel NMR spectra exactly. So what we found was that you have to include having larger degrees of variation in alkylated structures. One example is dibutyl ethylbenzene together with the methylbenzene together. So those kind of degree needs to be embedded into the surrogate to reproduce real fuel spectra. So those things can be seen if you're starting to look at the NMR spectra. And here I use very simplified low dimensional descriptors. But if someone wants, we can start to put the characteristics coming from detailed NMR structures into the whatever modeling approach. But the next question is that enough? Because once you're starting to throw out more parameters into the model, your model becomes sloppier, which means you always get good correlations, but you might not be able to follow the fundamentals.
Okay, the last question from Junxia. Thanks for the nice talk. You mentioned the fuel boiling is important in multiphase combustion. I was wondering for the time scale of evaporation tau. Did you estimate it with a boiling evaporation model, a normal evaporation model, or a mix of the two? There seems no information on the ambient temperature, also initial droplet temperature given in the slide. Thank you.
Okay, so in the timescale analysis, I utilized both. So I took very simple approach. I calculated thermal heat time through the heat flux balance. And then I also calculated this curve separately. I summed them up as a simple approach. And then if you do combined calculation, you're gonna get log behaviors, similar orders. And the analysis was performed assuming that fuel being at room temperature, 300 Kelvin. And then the vaporization temperature was around, the ambient air temperature was around 800 Kelvin to do that. Yes, it does change substantially depending on how you pick the temperature as well. But most of the combustors for the gas turbine combustors, their inlet temperature is around 800 Kelvin. That was the reason. And then the diesel combustor, once you go to the after the compressions, the air temperature is around 800 to 850 Kelvin as well. So
Okay.
there was justification for that temperature information.
All right. Okay. Thank you so much, Sang-hee. So that's all we have for today.